Well, hello, good evening, and welcome. My name is Roger Siegel, and I'm coming to you live from Sarasota, Florida, and welcome to AP Live tonight. This is AP Physics C, Electricity and Magnetism. And joining me is my friend and co-teacher, Kristen. Say hello, Kristen.
Hello, everybody. My name is Kristen Gonzalez Vega, and I am a teacher here in Frisco, Texas.
All right, well, wonderful. Well, it is, as I said, it's great to have you guys here. So since last time we were together, we did learn some new things from AP about the dates of the test and the format of the test. So as we get more information with that, we'll continue to share that with you. But we want to let you know that you can go to the AP website and find updates on all the tests, their dates, and how any changes that you might know about. I would say the most important update for us is, besides the time, is the fact that we're going to have an open note and an open book test. And so that really gives us a lot of opportunity to leverage all the information that we've gathered all year, whether that's notes or how your teacher has laid it out for you. But AP is counting on you to have access to that, not like they're asking you to, but they imagine that you will. And so I think as we get to studying and reviewing, and this is our first review session tonight, you want to think about organizing your information almost like a control panel, so that when you sit down to take that test on May 11th, you know where every piece of information is, you know what unit that's from. So if you have to look for something, you can do it really fast. So anyway, we'll talk about that more as we get into this. I know I'm really excited about creating some opportunities for my students in that way here in Sarasota, and I hope you guys can have fun with that too. All right, so I'm gonna jump in and start sharing my screen. And as I said, tonight is our first night doing review and getting you guys ready for the AP exam. Now, I did say May 11th, the AP, all of your AP exams have been pushed back 1 week from their original date. So yours was going to be on the 4th. Now it's going to be on the 11th, a Monday. And so we're going to, between now and May 1st, I'm sorry, we've got 4 weeks where Kristen and I are going to go through the entire curriculum and get you ready for this exam. And that starts tonight. So we're really psyched about that. Okay, so tonight, we're going back to day one, and this is probably day one of your class, whether you're taking a year long or a semester. This is day one for you, and electrostatics, charge, and Coulomb's law. And so if you, so let's just get started. So first, I want to say some things that you're going to learn from today. So we're going to talk about charges and positive charges and negative charges and static electricity and electrostatic forces and how they interact with each other. And we're going to explain and describe the behavior of a neutral object near a charged object. And then we're going to apply Coulomb's law. Okay. So this, of course, we assume that you have had this, this is review. So we assume you've had this class. And so we're going to kind of go through this real quick and then get to the meat. So first of all, we know that, all objects have charges because all objects are made up of electrons and protons and neutrons. However, most objects have the same number of protons and electrons, so they're neutral. If we change that balance, an object can be either positive or negative. If it has too many electrons, if it has more electrons than protons, it's negative, and vice versa. And if an object is negative, it will be attracted to a positive object, but it will repel negative objects, and also positive objects will repel positive objects. So like repels and unlike attracts. The things that allow charges to move, generally objects or substances that allow charges to move really easily, are conductors like metals. and charges, objects or substances that block the flow of charges are insulators. And one of the most important insulators is air. Air is a fantastic insulator. It's very hard to get a current to go through air, get charges to move through air, rubber, glass, plastic. These are all insulators. Okay, so electrostatics. So I want to talk about this, and this actually, you know what, we're not going to talk too much about this. I just want to talk about attraction and repulsion, because I know tomorrow night we're going to get into this in a lot more depth. But let's move on to our next little thing. I want to do a demonstration for you guys. So I'm stuck at home because we're in the middle of our quarantine here in Florida, as you probably are where you are, most of the world is. And so I was thinking, how am I going to demonstrate static electricity? Static electricity is one of the things that I've been demonstrating since I was a little kid, since I learned that if you rubbed your hair, rubbed a balloon with your hair, you could get the balloon to stay on the wall, to stick to the wall. That was pretty cool, right? So guess what? No balloons in my house. And I don't think that's an essential thing, balloons. So I didn't go out to get balloons. But I did go online and I saw somebody do this. So I want to show you what I have here. Let me kind of lean in here and take a look at this. And so this is a Coke bottle. And on top of it, we have just put a little needle or a pin actually coming out of the top of the Coke bottle. And I have a paper straw here. And I don't know if you can see this. I don't think so. But I've cut a little slot in the straw so that I can just balance the straw on the pin. And so with a little bit of finessing it, kind of like move it back and forth, you can get this thing to balance so well that we have a super, super low friction bearing. I mean, look at that. It's starting to already move a little bit. So I don't know if the air conditioning is on in here. It could be that. Always an issue when you have sensitive equipment. But look at this. We've created a really sensitive device. Now, how do you make static electricity? Well, one thing you can do, as I said, you can rub your hair with a balloon. I have neither hair nor a balloon. So, and I don't have a lot of sweaters here in Florida. So, but one of the best ways to make electricity is with Scotch tape. So if you take a piece of Scotch tape and you put it on top of another piece and then you pull them apart, you can create some good static electricity. So watch what happens. This is now a charged object. This is a neutral object. Okay. Watch what happens when I bring this close to, oh, look at that. Wow. See that? We've got some attraction right there. Let me try that again. A little bit of an attract. Oh, there's some attraction. If I come to this side, let's attract. Oh, there we go. And so you can see here that we can easily have these interact. Now this is charging. This is a positive charge. This is neutral. Why is it attract? Well, even though that this straw is neutral, it's made up of trillions upon trillions upon trillions of atoms. And those atoms have electrons, clouds around the outside, and nuclei in the middle. And when this positive charge gets close to these atoms that make up this paper, those atoms elongate a little bit. And the positive charges get, the negative charges get attracted. And so every little atom's electron cloud gets a little dipole, gets pulled apart. And so even though this is a neutral object, it'll still be attracted to a charged object. And so we'll play with that a lot more tomorrow. I think that's going to be a lot of fun. So that's what we do in our lockdown, physics teacher lockdown. Okay, now let's see. So the next thing I want to talk about is Coulomb's law, and then we're going to do some problems. So Coulomb's law is one of these fundamental laws that describes the interaction between charges, and it's fundamental because it's a force law. It's a field law. It tells us about over distance, how two things can interact with each other. So here we go with Coulomb's law. 2-point charges exert a force F on one another that is directly proportional to the product of the magnitudes of the charges Q and inversely proportional to the square of the distance r between their centers. In other words, the force electrostatic is equal to kq1, q2 over r squared. What does that mean? If I have a charge here and a charge here, okay, and this is positive, say, and this is negative, well, they're going to attract each other. And how much attraction is going to depend on how much charge is here, how much charge is here, and the distance between their centers. And we usually call that distance r. Now, I'm hoping, oh, and by the way, this k is called the Coulomb's law constant, which this should be a large C. Sorry, Mr. Coulomb. Okay. So this k is Coulomb's law constant, and it is 9.0 times 10 to the 9th newtons meters squared per Coulomb squared. Of course, it's on your formula sheet, and it's readily available to you. Now, so that is how Coulomb's law works. The last thing I want to say before we start doing some problems is I want to talk about, hopefully, when I was explaining Coulomb's law, I really, really hope that some of you went, wait a minute, that looks familiar. Did you say that? It does, because that is, check out, this is gravity. Now, we studied gravity in AP Physics C Mechanics, and I'm sure you've studied it in other classes if you didn't take that one. But the force of gravity, check this out, is some constant times the mass of one object times the mass of the other over their distance squared. How similar are these two relationships? That's interesting, isn't it? Coulomb's law and the law of universal gravitation are essentially, are mathematically the same. What's different is the substance. This is about how two masses interact. In the universe, if you have two masses, they will attract each other. This is about how two charges interact. If there are two charges in the universe, they will either attract or repel each other. End of statement, full stop. Okay, so of course, none of this means anything until we start to try to do some problems. That's really how we do that formative work, to really think about, okay, how does this make sense? So we're going to throw it over to Frisco, Texas, and Kristen's going to take it from here.
All right, thanks, Roger. And if you look at what those constants are and the magnitude of those constants, and I love comparing that too, because if you look at the universal gravitational constant, that's 6.67 times 10 to the negative 11th, and you look at the Coulomb's law constant, 9.0 times 10 to the 9th, you can see really like what the difference in those forces is and the magnitude of those forces. Okay, so let's do a couple practice problems here. So we have here two particles, each of charge positive q, and they are on opposite corners of a square that lies in the plane of the page. We're going to put a positive test charge, little q, here at the corner of the third corner on the square. So we want to look at this, and we want to know what direction is the net force on that test charge. So we need to look at them all individually. So I'm going to kind of color code these here. We're going to call that charge 1 up in that upper left-hand corner, and I'll color that red. We're going to say that the bottom right corner is charge 2. Okay, so if we want to know what the force on that point charge is, well, there are two interactions here going on. We have one interaction between Q on the top and Q on and our test charge Q. And if we want to draw the force on that, well, if they're both positive charges, then that test charge on the bottom is going to experience a repulsive force, right? Like charges repel. So there will be a downward force on that. So I'm going to call that force 1Q. You always want to develop a way that you can identify these different forces or interactions when we're talking about fields later on with charges or potential or whatever it is, energy. You always want to develop your system of keeping everything straight, because when we have multiple things going on, we want to have an identifier. So I always will do force with a subscript of what my two charges are with that interaction. Okay, and then we also have the interaction between little q and the bottom big Q. Again, we look, are they both positive? Is one positive or negative? If these are both positive, again, there will be another repulsive force on that test charge, F2Q. So if we now just draw that off to the side here again, I've got a force to the left, I've got a force down. Well, if we look at these same charges, we know that force is K, Q, Q, which would be little q, over the distance between them squared. Well, if we compare these two forces, they have the same amount of charge, same distance apart, so the magnitude of those forces would be the same. So if I have two forces that are at a right angle, how do we find that third vector? If we draw tip to tail, then our resultant will be down to the left, which would be KC here. Okay, if we go one step further here, how could we find what the magnitude of that force is if the force between each one of these is F? Right, so if we redraw, we had that force down, we had that force to the left. And so if these are the same magnitude of force, how would we find that resultant force? Well, we'd use Pythagorean Theorem. So the net force squared would be equal to the force between 1 and Q squared plus the force between 2 and Q squared. The magnitude of those two forces are the same. So really we can say that that net force is 2 times that force squared. And so then if we want to find if this is squared, if we want to find what that net force is, we have to square root both sides. And so we get 2 times the square root of F, which is D. Okay, so a lot of times we see these kind of problems like this, or we may see a triangle with the forces, but finding each of those forces, and still important to always draw your free body diagram first. Okay, let's bring in a little bit here of mechanics into play. So I've got a small sphere of charge, big Q, 2.5 times 10 to the negative 5th coulombs, placed at the bottom of an insulating tube. A pith ball of mass 0.04 kilograms carries a charge of 1.6 times 10 to the negative 7 coulombs, is gently lowered into the tube until it reaches equilibrium. What is the distance d the pith ball from the small sphere will be when it's in that equilibrium? Okay, some important words here, right? If it's in equilibrium, then we know the net force on that pith ball is 0. So if we take a look at what those forces are, well, the pith ball has mass. So we have that gravitational force acting down on it, mg. Then we also have this charge down here. And since there's two charged objects, there's going to be that electrostatic force between them. So we want to look to see, do these objects have the same charge or an opposite charge? Because we want to know which way that force is. So these vector quantities, it's really important to look at that direction. So if these are both positively charged, then we'd have that electrostatic force going upwards. And if it's in equilibrium, then we know they're equal. So we know that the mg down will equal that electrostatic force. And then we can plug in, well, the electrostatic force is simply K QQ over R squared. And in this case, we're going to say that's D squared. And so if we want to solve for D, we got to rearrange, and we get that D is going to be equal to the square root of K QQ over mg. So if we substitute that in, D is going to equal the square root of 9 times 10 to the 9th newtons meters squared per coulomb squared times my 2.5 times 10 to the negative 5th coulombs times my 1.6 times 10 to the negative 7 coulombs over the mass, which is 0.04 kilograms, times gravity, which 9.8 meters per second squared, or always also acceptable 10. So usually for in-class work, I always use 10 because it's easier to do the math. But if we plug that in and we solve, we should get a distance of 0.3 meters. Now, if you notice, here I just use positive, but I also want to talk about what if one of these were negative, right? So obviously, if one of these were negative, then there would be an attractive force and it wouldn't be in equilibrium. But when we're doing these equations and you're looking at these forces, we never want to plug in, or at least the way that I work through them, you can do it different ways, but I never plug in the negative into my equation. I draw my free body diagram, I determine which way those forces are. Do I add or subtract them? And then I put them all in this positive, because drawing the free body diagram is going to tell you which way those forces are and whether you're adding or subtracting them. What I mean by that is, let's look at an example if I had 3 charges. Okay, and let's say I want to know what the net force is on this center one. Well, that's due to those other 2 interactions, right? We've got an interaction between the positive and the negative here, which would be an attractive force on this one. So let's call this 1, 2, 3. Between 2 and 3, but there's also an attractive force between these 2 here, 1 and 2. Well, if I want to know what the net force is on that middle one, if those forces are in opposite directions, I got to subtract them. The net force on this guy would be equal to force 1, 2, 3 minus force 1, 2. But when I go in and plug in those charges, I'm not going to put a negative in my equation because I've already determined that direction of those forces. And so now everything becomes absolute value. So we're only determining the magnitude of that force at that point. It's kind of like when you're dealing with forces and kinematics, and if you've drawn your free body diagrams and know that mg minus ft, then we don't put in negative for the gravity in our equation. So same thing with the charges here. You draw the free body diagram to determine which way those forces are. Do we add or subtract? And then everything in the equation becomes positive. Okay, and then we've got practice 4 here. So we've got our charged ball, big Q, 9 times 10 to the negative 6 Coulomb, set on an insulating stand. A small sphere of mass 0.57 kilograms, charge negative 5 times 10 to the negative 6, hangs on the string, a distance 0.3 meters above the ball. And we want to know what the tension in the string is. So I'm going to give you just a second. I want you to draw me the forces acting on that small sphere that's connected to the string. So draw me the forces. Which way do they act? Hopefully you've got some paper there and are working along with us. And then write me a net force equation. So if you need more time, you can pause, but the first thing we always want to identify are those charges, positive or negative. And I'm going to always label it on my diagram. So the bottom charged ball is positive Q, and my top one is negative Q. So the first thing I'm going to draw in, well, if that's a negative and a positive charge, there's going to be an electrostatic force going down. But this also has mass. So there's also that gravitational force going down. And it's connected by the string, so there is tension going up. Okay, so if this is in equilibrium hanging here, then we can say then that the Ft up has to equal that electrostatic force plus the gravitational force going down. So tension will equal K big Q times little q over that distance squared plus mg. So if we plug that in, again, we get our 9 times 10 to the 9th times our big Q times our little q. Again, I'm not plugging in negative because I've already determined that direction. So that would be the gravitational force part plus our mg, where our mass is 0.57 kilograms times our acceleration due to gravity. So when we combine and add those together, you should calculate that the tension in the string is equal to 10.2 newtons. Okay, so what would happen if we switched the charge, or if we change the magnitude of the charge? We would change that amount of tension. So we'll kind of be doing a little bit more conceptual practice as we get closer to the test, but that's one thing that is going to be different about the exam this year, is that we are going to have to be able to explain things a lot more, because there will be less focus on calculations on the problems and more focus on the conceptual what's going on. Okay, which is kind of what number 5 is doing here. So number 5, we have 2 small spheres. that each have a charge q and are separated by a distance d. If the force on each sphere by the other has a magnitude of F, right? Newton's third law. If the sphere on the left has a force on it due to the sphere on the right, then the sphere on the right also has a force equal magnitude as the other one. So they each have a force on them that is F. So we want to know if the charge on each sphere is doubled and D is halved, what will happen to that force between them? Okay, so again, I'm going to give you a second, see if you can set that up and get an answer, and then we will talk about it together. Okay, so first we want to look at is our equation. Our relationship is that electrostatic force is QQ over D squared. So we want to put in a little coefficient. What's happening to each thing, right? So if each charge is doubled, well, I'm going to put in a 2 in front of each of those charges. And if the distance is halved, well, I've got half the distance. But we got to be careful because that bottom is squared, right? So we want to look at what's going to happen to the left side of the equation here. If I have 2 times 2, well, the top is going to be 4 times as much. But I have half the distance squared, which means 1/4. Well, 4 divided by 1/4 means 16. Well, if the right side of the equation is changing by 16 times as much, that's 16 times bigger, then the left side of the equation has to be 16 times as much as well. All right, so hopefully that gives you some good practice on those Coulomb's law equations. And I'm going to toss it back here to Roger to do some more AP style questions.
All right, thanks, Kristen. Well, great. Well, let's go ahead and do a couple of great problems to take us home for tonight on this beautiful Monday night. I hope you guys are doing great wherever you're listening from. So I have a couple of problems here to look at. Here's the first one. And this is just like the problems that Kristen just did with you. This particular problem has the force of gravity involved. So we're never far from force problems when we're doing physics. So here you can see we've got two small spheres, each at mass m and positive charge q, hangs from these threads of length L. And the thread makes an angle theta with the vertical as shown. Derive an expression for the charge q in terms of ml theta g and the Coulomb's law constant. All right, so let's take a look at this and see what we can do. The first thing that I would hope that you would want to do is I would hope you would draw a force diagram, because clearly this is a force problem. And so I say, well, let's pick one of these, and the symmetry of the problem will allow us to solve it from just one side. Okay, so if I look at this one on the left, this particular one, and I draw it over here, well, what are the forces that are acting on it? Well, there's the tension is pulling up at this angle T. Since this is happening on the Earth, this is the force of gravity, Fg. And then there's got to be a force pulling this to the left, otherwise it'd be accelerating to the right, and that is the electrostatic repulsion, Fe. And so that's your first step. Take your time and draw a good force diagram. Now, as soon as we get this, we know, that this is in equilibrium. It is not moving, not accelerating, and therefore all these forces have to sum to zero. And when your forces sum to zero, that means you get a closed polygon. And so this is T, this vector, plus this vector, plus this vector equals 0. Fe, T, and Fg. And we also know that this angle is theta. Now, another thing we do know is we know the length of this, but I wouldn't put the length on this triangle because this is a force triangle. We might need that in a minute, and we'll see what happens with that. All right, so we want to find the charge. And so you always want to ask yourself, where is the thing that I'm looking for? And the place where the charge would be found would be in the electrostatic force. I don't know the tension. The tension is not one of my given variables. So I want to kind of stay away from that. So I'm going to go ahead and, just kind of take him out of the game. We're not going to deal with the tension. We'll just leave it over there. We'll see if we need it later. All right, so now how do I relate these? Well, theta is one of my variables, so I can use that. And so I can say that the tangent of theta is equal to Fe over Fg. And remember, we said that the thing we're looking for, the Q, is inside of Fe. So let's solve it for that. Fe is equal to Fg tan theta. All right, now this is the electrostatic force, and we said that that is found by Coulomb's law. So that's K Q1 Q2 over R squared. Now, I don't know what R is, and R is not one of my variables, but I'm just going to hold it there for now. Later on, we'll have to come out and figure out what R is in terms of those variables. All right, and that's going to be equal to Fg, which is mg. Those are some of my variables in tan theta. And so I'm going to solve this for Q. Now, each of these Qs, they have the same charge and the same mass. So that's going to be actually kq squared over r squared is equal to mg tan theta. All right. Let's keep going. Now, we're solving this for Q, so that means that Q squared is equal to R squared mg tan theta all over K. All right, now, we're close, but I said we can't use R. So let's go ahead and look and see, where is R? Well, R is the distance between these two. And so R is this distance from here to here, the distance from these two centers. Well, let me just look at this value here. Let me call that value right now. Let me just call it X, which is half of R. Well, that is related to theta right? And this is X, this is my distance, and this is L. And so I said a few minutes ago, let's hold off on L. It doesn't go on the force triangle, but it does go on the space triangle, on the spatial relations triangle. And so let's go ahead and see what X is. And so it looks like the sine of theta is equal to X over L, which means X is equal to L sine theta, which means that R is two of those X's, or 2L sine theta. So let's just put a little box around there. So you'll see that came later. Okay, and so we're going to go ahead and add that in there. And so we'll say Q squared is equal to, well, let's just say Q. I don't want to say Q squared. And let's solve this for Q. And so let's say that Q is equal to the square root of all this. So that's going to be R times square root mg tan theta over K. And so R is 2L sine theta times square root of mg tan theta over K. All right, so that is our charge in terms of the other variables. So again, don't get bogged down in the math. It's not about the math. Make sure you understand the diagrams, and they have to be understood first before you start to pull everything else into it. All right, last problem of the night, of this beautiful Monday night, in wherever you're listening from. All right, so we've got two identical point charges, Q plus, sit on the y-axis at position 0b and 0 negative b. A different charge, Q plus, is on the x-axis at position d0. What is the net force Q from the two, on Q from the two Q plus charges? Okay, now let's go ahead and take a look at this and see if we can make some sense of it. We've got these two charges and we want to know how they're affecting this charge over here. Well, since these are both positive, this will feel a repulsive force in that direction, force electrostatic, from this charge, and this small charge Q will feel a repulsive force in this direction, actually symmetric, from this charge. And so each charge exerts this force. Now, our job is going to be to find out what that force is total, the net force. Now, I hope I can convince you without too much trouble that when we look at this, this electrostatic force, it's made up of a vertical component and a horizontal component, as is this one, made up of a vertical component and a horizontal component. And I'd like very much to convince you that these two cancel out. And that what we have to do is we have to look at this electrostatic force, force electrostatic, extract the x value, Fe in the x direction, and then double it because we have two of them. We have the x value here, and we have the x value here. And so I'm going to say that F net is 2 force electrostatic in the x direction. All right. So I'm going to start there. Again, one of the things I love so much about teaching physics is we get to use astronomy, we get to use algebra and calculus and geometry all together. It's great stuff. So this is 2FEX. Now, what is FEX? Well, I'm going to put this angle theta here, okay? Now, if you were to say to me, Mr. Siegel, there is no theta over here, so we can't use it, you'd be right. However, when you're doing a problem, you have to sometimes put some shortcuts in there. So let's let that be a placeholder. We'll hold on to the theta and we'll come back and fix it later, just like we did in the previous problem with the distance with the r. All right, so, well, this is theta, and these are related by cosine because the cosine of theta is adjacent over hypotenuse. So that's FEX over FE. And so that means that FEX is FE cosine theta. All right, so that gives me my relationship. So I'll come over here and I'll put that here. That's 2 FE cosine theta. Okay. Now, what is the electrostatic force from either this one or this one, right? It really doesn't matter which one I do because I'm just going to take one and double it. Symmetry allows me to make that shortcut. So, well, the electrostatic force is given by Coulomb's law. So that's going to be K, Q1, which is little q, Q2, which is big Q, all over the distance between them squared. Again, I don't know what r is yet, but I will know in a minute, times the cosine of theta. Let's just take those one at a time. We can't put an r in there. We can't put a theta in there. We'll do them one at a time. All right, getting there. We're really close. Now, this is 2K Q over r squared. Now, what is the distance between this dot and this charge? Well, if this is D and this is, I'm sorry, that's not correct. This distance here is B, and this distance here is D. Well, that means that this is, by Pythagorean theorem, the square root of B squared plus D squared. And so that's going to be the square root of b squared plus d squared, quantity squared, because I'm squaring the distance, and the distance is the square root of b squared plus d squared, times the cosine theta. I promise we'll figure out the theta next. All right, now we're almost there. So this is 2k q over, when I square this, I get b squared plus d squared. Now, what's cosine theta? Well, I'm going to come back over here, and I'm going to point out a few things to you. This is our theta, which is the same theta that I have here, which by vertical angles is the same theta here. So the cosine of this theta, cosine theta, that same theta, is going to be adjacent over hypotenuse. And so that's going to be cosine theta is going to be d, the adjacent to the theta, over the hypotenuse, square root of b squared plus d squared. And so that means that my final answer is going to be 2k q over quantity b squared plus d squared. And when I multiply b squared plus d squared to the 1 power, let me go ahead and to the 1 times b squared plus d squared to the 1/2, I add the exponents and I get b squared plus d squared to the 3/2 power. Now, one of the reasons that I really wanted to do that problem for you guys is because that is a problem that we see over and over again. The geometries that we see in this problem are geometries that you've probably seen before, even in other kinds of problems that we've done. So hopefully that got you something and reminded you of where we are and where we're going. All right, so today we said we were going to describe the behavior of charges, systems, and interacting with each other. And we said we would describe the behavior of neutral objects in the presence of charged objects and systems of charges and apply Coulomb's law. I think we did that. And so, really, again, thank you so much for showing up and for the hard work that you're putting in. It's really always an honor to work with such great students to be an AP teacher. Kristen, what are we going to do tomorrow?
Tomorrow, we are going to learn how all these charged objects became charged, in what different ways we can charge objects. And we're also going to explore electric fields and drawing field lines.
Excellent. Wonderful. So that's what we have for tonight. Thank you again for tuning in. I'm Roger Siegel from Sarasota, Florida, and happy physicsing.
Have a great night.